Recurrent neural networks or RNNs are a kind of popular neural network that specialize in processing sequences. They are often used in natural language processing as well as time series related tasks. In this video, I'll help you understand how they work. So without wasting any further time, let's get started. But hey, hold on. It would be really motivating if you can press the subscribe button and also press the bell icon to be notified for amazing videos on data science and machine learning. With that, let's kickstart the discussion. So now, let's discuss more about how RNNs work. RNNs basically iterate over multiple inputs and keep updating a state called as the hidden state, which is known as h of t. The current hidden state, which is h of t, is calculated using the previous hidden state, which is h of t minus 1, and the current input x of t. The output y of t is calculated using this hidden state, that is h of t, that we just calculated in the current step. If this idea is clear to you, let's discuss about the basic RNN cell. Well, this is how a simple block of recurrent neural network looks like. Now what exactly makes recurrent neural network recurrent? Well, it uses the same weights for each step. As you can clearly see, there are three sets of weights that a recurrent neural network uses. The first set of weight is what is called as Wx of h. It is used to connect the input to the hidden layer, that is x of t and h of t. The second set of weights which I used are WHH, that is connecting my previous hidden state to the current hidden state, and the last set of weights are also called as WH of Y, which is used to connect my hidden state to the output state. We also use two sets of biases in our RNN. The first is B of H, which is added when calculating the hidden state value. The second, which is B of Y, is used when we calculate the final output value at the current time t. Now the block that you see in F is essentially an activation function. For the given task, I'll be utilizing the tanh activation function, and yeah, this is the overall structure of how an RNN looks like. So if you look closely, there is a dotted line that I've used to connect h of t and h of t minus 1. So this is where your hidden state is again fed back to your neural network structure. So what happens essentially is you start off with some randomly initialized weights or randomly initialized hidden states. After every iteration, the hidden state keeps updating, and the update at the current state depends on the hidden state that you used previously. So this is how the RNN works in general. If this idea is clear to you, let's move forward and look at how RNNs work with respect to equations. So the basic RNN block can be described using two equations. The first equation is calculating the hidden state at time t. So the hidden state at the current time is equal to tanh h, which is the activation function, and the input to the activation function is the sum total of first a multiplication of wxh with x of t, that is the current input at time t, plus whh, which is the hidden state matrix, into h of t minus 1, that is the hidden state that was recorded previously in the previous timestamp. And last but not the least, you also add the bias term to the overall equation. Once you've managed to calculate the value of h of t, you go forward and you multiply this hidden state value with the weight value, that is wh of y, add the bias to it, and you get the final output, which is y of t. Now this is for one single iteration. It also depends on what kind of RNN you are using. Are you using a many to many, or are you using a many to one kind of an RNN, which is widely used when you think of sentiment analysis? So in that case, what happens is you iterate over this process multiple times, and finally once you reach at the end of the sequence, it is here that you will get your final output in case of many to one RNN. The reason why I laid a lot of stress on many to one RNN is because the example that I have in mind is also corresponding to a many to one RNN. Now let us discuss about the shapes of the different matrices that I just mentioned previously. So the first matrix is the WHH matrix, which is nothing else but the hidden state matrix. The size of the matrix is dependent on the hidden size that we have defined. The larger the size, the more you can fit in parameters here. So essentially the shape of WHH is hidden size comma hidden size. So essentially if your hidden size is say 2, then you will have a 2 cross 2 WHH matrix. The next matrix that I want to talk about is WXH, that is your matrix connecting the input layer to the hidden state. The size of this matrix is hidden size comma input size. So if your hidden size is 2 and if your input size is 20, then your WXH matrix would be 2 comma 20. Next up we have the WHY matrix. These are the weights that connect my hidden state to the output state. Now the weights defined is you have output size comma hidden size. So if your output size is 2 and if your hidden size is 3, then my shape of WHY matrix would be 2 comma 3. Last but not the least, I'll have shapes of my biases, that is BH and BY. The corresponding shape for BH and BY would be hidden size comma 1 and output size comma 1 respectively. Hopefully if the matrix dimension idea is clear, let's proceed forward. What I intend to cover next is I want to give you an idea of how an RNN functions from within. I will cover the forward propagation step once the training has happened. I won't cover the back propagation step in this video. If you want me to create a back propagation based video, do let me know your thoughts in the comment section of the video, and basis the feedback, I'll create another video on the back propagation of RNNs. So without wasting any further time, let's discuss what the task in hand is. So imagine I have a sentiment analysis task wherein my overall vocabulary consists of 20 words. I've taken different combinations of those 20 words and I've trained an RNN to detect if the given sentence has a positive sentiment or a negative sentiment. The RNN that I created had the following details. The hidden size of the network was 2. The input size given my vocabulary size was 20, so the input size turned out to be 20 as well. And last but not the least, I have output size set to 2, which is owing to the fact that my sentiment analysis task has two classes, negative and positive. The next thing that I did after defining the sizes was I trained my recurrent neural network for 1000 epochs for the given training dataset that I had, and these were the weights that I was able to compute using the training process. The first matrix that you see here is WHH. It is a 2 cross 2 matrix and it is the same matrix that is a connection between the previous hidden state and the current hidden state. The next matrix is WHY, which is again a 2 cross 2 matrix. The third matrix is WXH. Given my input size contains 20 unique characters or 20 unique words, so that is where my WXH is nothing else but a 2 cross 20 matrix. So it consists of 2 rows and 20 columns. I also have two bias matrices, that is BH and BY. Both correspondingly have a size of 2 cross 1. And last but not the least, I've initialized my overall previous hidden state matrix, that is h of t minus 1 to 0 0. Let's now go forward and look at how a prediction would be made using an RNN. Consider the sentence I am sad. So I is one word here, am is the second word and sad is the third word. So in total I have 3 words in this sentence. So how is the overall final output created is what I'll walk you through. So the first thing that we'll calculate is we'll calculate the hidden state value for the first input, which is the word I. So I start off by computing h1, which is np.tanh, and I supply the input values, which is wxh dot input of 0 plus whh dot h of t minus 1 plus b of h. Now if you recollect, WXH, WHH and WHY would be a constant after the training has occurred. So right now the only thing that will keep changing every time would be my hidden state value. So in the first instance, when my word is I, my X value or the X matrix that you see here is essentially a one hot encoded matrix with 20 rows and 1 column. 19 values would be zeros and only one value located at location 13 would be 1. My WXH would be the same. So if I consider the first part of the equation, that is I am multiplying two matrices, that is WXH, which has a dimension 2 cross 20, and my input vector, which is X, that is 20 cross 1. The resultant would be 2 cross 1 matrix. Next up, I have WHH multiplied with H of t minus 1. So a 2 cross 2 matrix multiplied with a 2 cross 1 matrix would result into a 2 cross 1 matrix. Similarly, the bias term that I have, which is again a 2 cross 1 matrix, would add up together to give me the final state, which is H1, and the value of H1 is minus 0.94 and 0.88. It's again a 2 cross 1 matrix. If the first iteration is clear to you, let's move on to the second iteration. But before we jump onto the second iteration, one thing that I want to specify is if it's a many to many RNN, then you will have a corresponding Y output at this stage as well. But given it's a many to one RNN, since we want the sentiment at the end of the sentence, we'll have just one output, which is after all the iterations are complete for this given sentence. So if this idea is clear to you, let's jump on to the next slide. Now I jump to the second word, which is am. A lot of things would remain a constant, that is all my weight values, that is Wx of h, WHH and B of h remain a constant. The only modification that happens in case of the second word is my input changes. So am would be represented again by a 20 cross 1 matrix where it will have 20 rows and 1 column. 19 values would be zeros and 1 value would be 1. And here for this particular word, I'll have 1 located in the 10th location. The same set of calculations follow and I'll get a corresponding hidden state h of 2. Now, once the second hidden state is computed, I'll move on to the final word, which is sad. Now, once I jump to the final word, which is sad, the only changes that I can observe is my input value would change. That is, I'll use the one hot encoded representation for the word sad. Secondly, my hidden state value that is fed in, that is, I'll now use H2 rather than H1. So H2 is something that I'll be utilizing right now, which I computed in the previous step. And using this set of calculation, I'll generate the third hidden state value. Now, once the third hidden state value is generated and I know for a fact that I've reached the final word of the sentence, it is here that I'll now compute the value y. So I'll take the hidden state value, I'll multiply it with the vector why and I'll add the bias term to compute y. If I have to talk about the dimension of the matrices, so why, which is a 2 cross 2 matrix, when multiplied with h3, which is a 2 cross 1 matrix, will give me a new matrix which is again 2 cross 1. This added along with the bias matrix, which is 2 cross 1, will give me a final matrix which is 2 cross 1. Now, if I have to compute the final output, that is the sentiment of the sentence, then all I have to do is I'll have to calculate the softmax value of the two values that are there in this matrix and find out the argument with the maximum value. So essentially what I get after this calculation is class 0. So it's clearly evident that the sentence is a negative sentiment sentence. So yeah, this is something that I wanted to demonstrate with respect to how RNNs work after you've kind of used Keras or the other libraries that are there. I wanted to go under the hood and not speak about backpropagation because that would have been a bit too much to digest in one go. But yes, if you really want me to cover backpropagation as well in the same manner that I've covered the forward propagation, feel free to drop in a comment in the comment section below and I'll surely create a video around backpropagation if there are a good number of people who want it. So yeah, this is all that I had in terms of how RNNs work. I hope you enjoyed this video. If you do like the content that I create on my channel, it would be really motivating if you can press the subscribe button and also press the bell icon to be notified for amazing videos on data science and machine learning. Thank you so much for watching this video.